Good morning, everybody. Welcome to the webinar. We will be starting in a couple of minutes. Let's give everybody a couple more minutes to join, and then we will start our webinar this morning. Okay. Good morning, everybody. Good afternoon, wherever you are around the world. And let's begin today's webinar. This is the last webinar in our series of advanced Event Horizon Telescope data analysis techniques. And it will be on the principal component analysis techniques for model comparison and imaging with Event Horizon Telescope data. As I said, this is the last of this series webinar. We're at the end of our semester. And if you would like to find the recordings of all the previous webinars of this series and the previous ones, I just posted on the chat the link to the YouTube channel. We will have another really exciting series this coming fall. So if you want to get information, please go on the website and look for the announcement for when it comes for next semester's webinars. Today's webinar will last about an hour, and Lia has put some, our speaker has put some breakpoints in the middle of the presentation. So if you have any questions, he would be happy to answer. Please post any questions that you have in the Q&A feature of the webinar, of the Zoom webinar. I will facilitate those questions, and our speaker will be happy to answer them. And at the very end, we will have a little survey, a very, very short survey for everybody to respond to. And these are extremely useful for our project and for our organization, because this is how we know what worked and what didn't, how to improve our webinar series. And we would really, really appreciate it if you could share that with us. It is my great pleasure, without any further ado, to introduce today's speaker, Dr. Lia Medeiros. Lia is an NSF Astronomy and Astrophysics postdoctoral fellow at the Institute for Advanced Study in Princeton, New Jersey. And she is also the lead for the Gravitational Physics Input Working Group of the Event Horizon Telescope. Lia is working on developing simulations of accreting black holes, as well as modern state-of-the-art algorithms to compare those simulations to the data and use the data to, as we will find out today, to image the black holes that we observe with the Event Horizon Telescope. She also has done a lot of work in modeling black holes in theories of gravity beyond general relativity, and ask what would the observations be like if Einstein was not 100% right. Today, as I said in the beginning, she's going to talk to us about a new technique that she's developing that involves principal component analysis for model comparison and imaging with Event Horizon Telescope. And thank you very much, Lia, for doing this. And please go ahead, start your webinar.
Great, thank you so much for that really wonderful introduction. Let me share my screen here. So thank you everyone for coming to our webinar. I am very happy to have the opportunity to get to talk to all of you today. Oh, I am actually at the end of my webinar, so spoiler alert. 1 second. Let me try that again. Okay, this looks better. Okay, so as I was saying, I'm very happy to be able to talk to all of you today about how we can use PCA to perform some imaging and model comparison with EHT data. Before I move on from my title slide, I want to explain to all of you what it is that you are all looking at here. So this is the result of a general relativistic magnetohydrodynamic simulation, or GRMHD for short. And after we run the GRMHD part, which calculates how the flow moves around the black hole and how the plasma is going to be interacting with the magnetic field of the black hole, after we run that simulation, we then ask ourselves what would be happening to the photons, right? And so we have the second simulation that calculates the radiative transfer and ray tracing. And this particular animation is actually a free color image. So everything that you see in blue corresponds to 1.3 millimeter wavelength emission, and that's the wavelength that the EHT observes at. Everything you see in green is 0.8 millimeter wavelength, and I know that it's hard to see the green, but just keep in mind that everything you see in blue is actually more of a bluish green. So the 0.8 millimeter emission is kind of coincident with most of the 1.3 millimeter emission. And everything you see as red corresponds to 3 millimeter wavelength emission. And of course, the structures that you see as white, in particular this ring structure here, this is telling you that these structures are achromatic, at least in the wavelength range that we observe, that we are probing with this particular free color image here. And so I know that most people on this call are probably part of the EHT, but just in case we have some new EHT members or some people that are not EHT members, I just want to take just a couple slides to give you a brief introduction for how the EHT actually works. So the EHT is a very long baseline interferometer. And the way that this actually works in practice is that each pair of telescopes will observe a specific location in the two-dimensional Fourier domain. So the idea here is that you have your source image, and then you're going to take the two-dimensional Fourier transform of that source image, and this will give you this two-dimensional Fourier space that I'm showing you here on the right. In VLBI, we like to call the Fourier domain UV space, so I might use that term as well. The distance from the center of the Fourier domain is going to tell you the frequency that you are observing at. So if your telescopes are farther apart, you're going to be observing a higher frequency. You're going to be farther from the center of the Fourier domain. And in terms of an actual image, what that means is that if your telescopes are farther away, you're going to be probing a smaller scale structure in your actual image or a higher resolution. Now, of course, we also use the fact that the Earth rotates as part of our instrument. And so as the Earth rotates, each pair of telescopes is going to be in a slightly different location relative to the source that we're imaging. And also as the Earth rotates, you're seeing that other telescopes come into view. And so we're creating some additional pairs as well, right? So each pair, instead of just observing one location in the Fourier domain, will actually observe a curve as we're showing here. And so I wanted to talk a little bit more about our interferometric baseline coverage. And so I'm showing you here on the left an example snapshot from a simulation, and the middle panel is showing you the amplitude of the complex Fourier components of that image. And on the right, I'm showing you the phase of the complex Fourier components of that image. And here, if you look at the structures that you can see in the amplitude of the Fourier component, which again, in VLBI, we call the amplitude of the Fourier components visibility amplitude, and the phase is visibility phase. And so you can see that there are these concentric rings that you see in the visibility amplitude here, right? But if you look at only the parts where you would actually be able to observe, this is all that you would see. And so the point here is that there is a lot of space that we cannot probe, right? There's a lot of regions in the Fourier domain, like for example, this gap right here, where we do not have enough telescopes to probe, at least with the 2017 EHT, which is what I'll be talking about today. So I'm going to be focusing specifically on the observations we did in 2017, and then the results that we published later on in 2019 for the images of M87, for example. And so the same thing will happen with phase, right? So we're only going to be able to collect data for a very small part of the overall Fourier domain. And so because we have such sparse coverage, there are a lot of unique challenges that we need to deal with when we try to analyze this data, to compare it to simulations or to try to reconstruct an image, for example. And so that's really the motivation of most of what I'm going to be talking about today, is this really sparse interferometric coverage. And so in the publications that we published in April of 2019 with the first M87 results that I'm showing you right here, we used three main analysis methods. And I'm going to go over each of these methods briefly and focus on kind of the pros and cons of each of these methods. And then when we talk about this new method that we're developing, we'll be able to compare that one to these other three methods as well. And so first, we're going to talk about image reconstruction. In those first papers, we included 3 different image reconstruction algorithms, but I'm only going to be talking about the maximum likelihood methods today, which are 2 of the algorithms. I'm not going to be talking about the details of how the clean algorithm works. So for the maximum likelihood methods, what you're really doing is you start off with a grid of pixels, as I'm showing you here on the left, and you're going to try to add some intensity to these pixels. And then as you add different regions of intensity to the pixels, you're going to take a Fourier transform of your image, and you're going to compare that Fourier transform to the M87 data that's shown here on the right as these red dots. And on the bottom of the slide, I'm also showing you the actual equation that these algorithms are trying to minimize. And I want to specifically point out that these algorithms also include weighting functions and regularizers. And so one of the really important things to keep in mind when we're talking about imaging with EHT is that there are technically infinite number of images that can be consistent with our data. And so we need to choose which of these infinite images we think is most likely, right? And so this is what these algorithms are trying to do with these different regularizers. The other part of this is that because you have so many pixels, you have a lot of free parameters. And so you also need to use these regularizers to try to handle this large number of parameters as well. So for example, some of these algorithms will use regularizers that will prefer the emission to be kind of localized in the center of the image, for example. Or other regularizers might prefer smoother images. They might minimize the gradient in the image, for example, which essentially just means that pixels close to each other will be very correlated. And so I'm going to take you through a few iterations of this software here. And the 2 curves that you see on the right panel, this is the visibility amplitude of the image that I see on the left. So we're going to see how this algorithm will change the location of the intensity of the pixels to try to better approximate the data on the right. So we're only going to go through about 25 iterations here, but already you can see that we're doing a pretty good job approximating the data. And the image already looks quite similar to the image that the EHT actually published. And so as promised, I want to talk about the pros and cons of this algorithm. So the first thing that's really important is that it's a really general algorithm. So we're not baking in any assumptions. And so it's completely model independent, which of course is super important for what we're trying to do with the EHT. The cons, however, I've already mentioned a couple of these. So you have a really large number of parameters because you have a large number of pixels. You also need to make choices about which images are more likely, and many algorithms will, as I mentioned, prefer smooth images. But if you remember the images that I've been showing you from GRMHD simulations, we actually see significant gradients in those images. And finally, these algorithms can also create artifacts in the images. And so the figure that I'm showing you on the left here is meant to illustrate this last bullet point about these artifacts. And so this is a figure from paper 4 from the first EHT publications. And the top row is just showing you a few different geometric models. And we performed a simulated observation of these geometric models and then tried to reconstruct an image from those simulated observations with the 3 different imaging algorithms that we used for those papers. And so the 2 maximum likelihood methods are the 2 bottom rows. And as you can see, there are these knotty structures, let's say, along the ring here, even though you started off with a uniform ring. And so the way that you can think about this is that you're essentially, you have these 4 kind of bright spots along the ring, which again are very similar to the bright spots that we see in the M87 image that we actually published. And so this is something to keep in mind as we talk about the pros and cons of all of these algorithms and methods. So the second analysis method that we considered or that we used was a geometric model fitting method. And so the idea here is that you're trying to fit a geometric crescent to the data. And some models will also add additional Gaussians, for example. So the model that I'm highlighting here, again, these are figures from the first EHT papers. And this model has a Gaussian and it also has has a crescent and it has 2 additional Gaussians as well. So this is just one example. And so in a more recent paper that I was involved in, we looked at what the possible limitations of using these geometric models are, and specifically looking at the fact that these geometric crescents are significantly more simple than the structures that we see in the simulations. And so we wanted to understand a little bit more about how about what happens when you're trying to fit a image that is more complicated than a crescent with a crescent. So I'm going to show you 3 examples. The first example is what we consider the easy snapshot or the simple snapshot. This snapshot can quite easily be fit with a crescent, and this is what the crescent fit looks like here on the right. The middle panel is showing you what that same snapshot looks like when we pass it through a Butterworth filter. And so we are blurring this image with a Butterworth filter, not a Gaussian filter, because the Gaussian filter can actually introduce a bias in the overall ring diameter. And it is actually going to suppress some of the power in the regions that we actually have baselines. So it will lose some of the power that we want to keep, and it will keep some of the power that we don't want to keep. Whereas the Butterworth filter keeps more of what we want and loses more of what we don't want. And so we prefer to use the Butterworth filter, and that's what I'll be using throughout my talk. And so the second snapshot that we considered, all 3 snapshots, by the way, are from the same exact simulation. They're just different times within that simulation. The second snapshot is what we consider to be a medium difficulty. And this is what that snapshot looks like right here. And again, I'm showing you the filtered snapshot over there. And the result from trying to fit a crescent to the snapshot is shown here at the bottom. And so because this snapshot has a little bit more structure, and again, keep in mind that when you compare the actual filtered images from this snapshot and the previous one, they really don't look that different, right? So you might not think that there's additional structure, but remember that what we're really dealing with here is in the Fourier domain. So whatever small changes happened in this snapshot had a significant effect in the Fourier domain and made it much harder for us to actually fit this crescent. And so you end up with a result that is significantly biased, right? So you're creating a ring that's bigger than what we actually see in the original snapshot. And it's also much thicker than what we see in the original snapshot. And so we tried to add an additional Gaussian to this crescent model. And by adding this Gaussian, we were able to fit the diameter a little bit better, and the width of the ring is also a little bit better, but we're creating this structure here that seems to not really match any particular structure that we see in the original snapshot. So this is still a significant bias in the sense that we're creating a structure that we don't really see in the original source image. And so finally, we have the difficult snapshots, snapshot free here. And again, I'm showing the original snapshot, the filtered, the result from fitting a simple crescent, which looks really horrible, and the result from fitting a crescent plus a Gaussian. And even though it does look better than what happens when you just fit a crescent, the result from fitting a crescent and a Gaussian is still significantly biased away from the actual original image. And in particular, we're creating a ring that's much bigger than the original ring in the source image. And we're creating this additional structure here with the Gaussian that doesn't really seem to match any particular structures in the image. It's kind of in the same general region as some of these structures here, but it's not really doing a very good job of actually approximating those structures. And so the pros and cons for this method: first, you have a very small number of parameters, which is really wonderful. Second, it doesn't create the artifacts in the image that we were seeing earlier, right? So it doesn't want to, for example, divide your ring up into 4 different bright spots, let's say. The cons, however, is that it might be too simple for some of these snapshots that we see in these simulations. And so it might not adequately represent the data. And if it doesn't adequately represent the data, then it can be prone to the biases that I've been showing you here. And so finally, the third analysis technique is based on GeoMHD simulations. And so what we did for this is that we used a large set of simulated snapshots, and we actually compared each and every snapshot to the EHT data, and we allowed the snapshots to be scaled up or down, and we allowed them to rotate while we were doing this comparison. And then we kept track of how many snapshots in any particular simulation were close enough to the data. And the point of the movie that I'm showing you here is that, as you can tell, there's a lot of significant structural variability within any particular simulation. And so what this means in practice is that it's really hard for you to actually compare any particular snapshot with another snapshot and tell whether or not they came from the same simulation or not. And so the way that I like to explain this is that you have stochastic structural variability that is caused by the turbulence in the flow. And so when you look at a snapshot, you are looking at one particular realization of the turbulence. And there's no reason to expect that when you run a simulation for, let's say, 10,000 M, there's no reason to expect that you have probed the full range of possibilities for image structure that that particular set of parameters could reproduce. And so I wanted to dive a little bit deeper into this problem here. So the bigger image that you see on this slide that's kind of towards the top, this image here, this is the average from a simulation. That simulation is a MAD simulation. And at the bottom here, I'm showing you 14 different snapshots. But the catch here is that only 12 of these snapshots actually come from the same simulation that I used to create this average. So the average comes from a MAD simulation, which stands for magnetically arrested disk. And that's a simulation where the magnetic field is very strong and it's very ordered. And the other 2 snapshots that are somewhere in the middle here, those 2 snapshots come from a sane simulation, and that stands for standard and normal evolution. And that is a simulation where the magnetic field is significantly less strong and significantly less ordered. So even though these 2 simulations are in a significantly different regime as far as what their magnetic fields are doing, I want you to look at these 14 snapshots here and try to find which 2 snapshots you think do not come from the simulation that was used to create this average. So I know it's very hard to do any sort of interactive activity over Zoom, so we're not going to really have you guys guess, but I want you to guess in your head and think about which of these snapshots are different from this average image. I'll give you a couple more seconds. Okay, so here are the answers. These two snapshots are sane snapshots, and all the other parameters for these simulations are the same. The difference really is just mad versus sane. But again, hopefully this illustrates how hard this really is in practice, that it's really hard if you have, for example, this snapshot, which again, keep in mind that when we observe M87, we're really just observing one particular realization of the turbulence of M87. If you had, for example, this snapshot, it would be very hard for you to tell whether or not this snapshot is consistent with this model or not. And if you were to compare the snapshot with all the models, all the snapshots of a particular simulation, it's really hard to have a simulation snapshot that's actually going to match what you see with the actual source image. And so again, pros and cons for this method. So it is based on real physics. And so the parameters have physical meaning, which is of course very exciting and very important. But the cons, as I've been mentioning, is the fact that you're dealing with this stochastic variability where the source structure is changing significantly due to turbulence. And so it's very hard to compare any particular snapshot to another. And so what we have been working on is developing an alternative to these three methods. And so the idea here is that we're developing a fourth method that's orthogonal to the first three. We're not necessarily trying to replace any of the first three methods. We're just trying to find a different way to analyze this data that could be complementary to the other analysis methods. And the way that we have gone about this is creating an algorithm that will perform an image reconstruction, but it will do it in such a way that it is preferring images that are consistent with the broad kind of space of images where all of the GRMHD simulations lie. So we want it to be broadly consistent with simulation results without requiring that it is consistent with any particular realization of the turbulence of the source, because again, the source realization of turbulence might not match the realization of turbulence that you have in the simulations. And so as I'm talking about this, I'm also going to be highlighting a few other ways that PCA can be used for data analysis in the EHT, in addition to doing this image reconstruction. And so I've been talking about PCA, or principal component analysis, a lot, but I haven't actually defined it for you yet. So what PCA actually does is that it diagonalizes the covariance matrix to find an eigenbasis that is ordered such that the first few principal components explain the majority of the variance. Now, I know that's kind of a mouthful, so I wanted to also explain this using a simple, hopefully intuitive example here. So let's say that you have the data points that are shown here on the right. And this is a very simple data set. It's just two-dimensional. And so we've plotted it on these two-dimensional axes here. Now you want to apply PCA to this data set, and your results of applying PCA are going to look like this. So these are going to be your two eigenvectors. And I've changed the length of these two vectors to correspond to their relative importance. So the longer vector is the principal component. It is going to explain the majority of the variance in your data set. And the second principal component is going to be orthogonal to the first. And so just in this simple example, you can see that the longer PCA component is going to be aligned with the direction where you have the greater spread in your data, right? So the direction where you have the majority of the variance. And so what this means in terms of actually putting this into an algorithm is actually quite simple. So this is just a very simple linear algebra equation. And so if all of your data is contained in a matrix A, all you have to do is multiply the matrix A by its transpose, and that will give you the covariance matrix of your data. And then you just need to diagonalize the covariance matrix, as I'm showing here. And so the eigenvectors and the eigenvalues that you get from diagonalizing this matrix are going to be your PCA components, which are the eigenvectors. And the eigenvalues are going to tell you the relative importance of the PCA components. So they are going to encode essentially the percentage of the variance of the data that each PCA component explains. And so this example, of course, is very simple. But what we're really dealing with is a situation where we have a much higher dimensionality space. And so the way that you should be thinking about each of these images that live in this space of images is really as vectors, right? So each image is going to be a vector that's going to have the dimensionality equal to the total number of pixels in that image. And so all of your images live in this kind of hyperdimensional space, but unfortunately I can't draw a hyperdimensional space. So I've simplified it and put it on these three-dimensional axes here, because that's the best I can really draw, especially in Keynote. And so what we're going to do is we're going to use PCA to find the first free PCA components that I'm showing you here. So what we've done is we found a basis for this space. Now, if you only use free PCA components, you're going to be doing a really significant dimensionality reduction. So you will be losing a lot of your of the structures in these images. But I wanted to go through this exercise to show you that even with free PCA components, we can already do a significantly good job of approximating these images. So this is the same snapshot that I was showing you earlier. This is the simple snapshot from before and the filtered simple snapshot. And if we try to use this snapshot as a vector and we're going to project it onto this three-dimensional space that we've defined here with PCA, what we will have is a linear combination of these three vectors will approximate that image like this. And so already we know that there are a few things here that we're doing a pretty good job at. So we can reconstruct the overall size of the ring and the relative width of the ring. And we can reconstruct the location of the peak brightness around the ring as well. But obviously free PCA components really can't do that much for you. So what happens if we use a higher number of PCA components, let's say 20? So I am now projecting my vector onto a 20-dimensional space, and this is what the result of that looks like. So we can reconstruct, for example, this structure right here that corresponds to that structure. We can also reconstruct this structure, which I know is probably faint over Zoom, but I promise that there is a light structure right there that corresponds to this light structure right here. If you use even more PCA components, you can do an even better job. So here, you're also going to be reconstructing this structure, which is right there. So what I want to do now is I want to take you guys through a couple examples of how you can use PCA to understand more about the simulations themselves. And then we're going to get back to how we can use PCA to actually perform this image reconstruction that I've been talking about. So I think that this is a good spot for us to take questions if we have any. Any questions about what PCA is and kind of how it can be applied to images?
Yes, please feel free throughout the presentation to put your questions in the chat or the Q&A. I haven't seen anything yet. Just give a few seconds in case somebody would like to do it. Why don't you go ahead, Lia, and then we will continue at the end of the presentation.
Sounds good. Okay. So here in this example, we have applied PCA to 3 different simulations, and we've done PCA on each set of images from each simulation separately, okay? And so I'm showing the free simulations as these movies here on the left, and already you can tell that the overall morphology of the images in each of these simulations is quite different, right? So this was obviously done on purpose. We wanted to probe kind of how different image morphologies would behave with PCA. And the 4 columns that you're seeing here on the right, these are the first 4 PCA components of each of these models. And so there are a few things that you can learn about how these simulations vary just by looking at the PCA component. So specifically, if you look at this PCA component right here, it's going to tell you that one of the ways in which this particular simulation varies is that this structure here, this ring-like structure, will become brighter or dimmer. And this structure right here, which is actually the base of the jet for the simulation, will become brighter and dimmer. And again, if you compare that to what you're actually seeing in the movie, that does seem to be one of the main ways in which this particular simulation varies. And so you can do the same thing for the other simulations. Like, for example, this one here is telling you that the structure will become thicker and thinner, which again, you can see that this part right there kind of gets brighter and dimmer. You can see right here that this part is going to get brighter in number as well, and that you will have these structures here, which are really kind of the edges of the funnel region that will come in and out of view, will get kind of lit up and then faint again. And so the other thing that you can do already is you can use the eigenvalues to learn more about how variable each of these simulations actually is. And again, all of this is really focused on morphological variability or structural variability, in contrast to what's happening to the overall flux. And so, for example, if you look at each of these panels in the top left, I also include the eigenvalue for that particular component. And what we've chosen to do here is that when we apply PCA to these images, we don't subtract the mean from the images. And so the first PCA component is very close to the mean. And the first eigenvalue tells you how important that particular component is. And so in this particular implementation, it's telling you how much of the variance the average image explains for these simulations. So if you compare, for example, model B, which is at this top row here, the average image only explains about 66% of the variance. And if you look at the bottom here, the average image explains about 88.5% of the variance. And so if you compare those two simulations, you can tell that the top simulation has significantly more structural variability than the bottom simulation. So this is a way to quantify structural variability within a set of images so that we can actually compare different simulations and compare how variable they actually are. And so the other thing that we did was also look at the spectrum of the eigenvalues. So again, the same three models, we're just looking at how the eigenvalue spectrum looks like for these three models. So the first thing that you notice, of course, is that the first principal component dominates, as we already saw. And the first few components account for about 90% of the variance. So these dots that you see along the curve, this is showing you how many PCA components you need to account for about 90% of the variance. And the final thing that you notice is that the higher components explain very little variance. And so this is why PCA is so powerful for dimensionality reduction, is that the higher order components explain such a small percentage of the variance that you can usually neglect them and not really lose too much of the information in your original data set. And the other thing that we noticed is that the slope of these three different spectra is very similar, right? And so we were wondering why that is when the actual morphology of these images is quite different. And so to explore this further, we used a particular power spectrum, right? So you define a power spectrum as an equation, you have some free parameters, like for example, the slope of the power spectrum might change. And we created a decent amount of red noise images that would have particular power spectra. And so here's just an example of 4 of these images is what these look like for a particular set of parameters for our power spectra. And what we were able to show is that the power law index of the PCA eigenvalue spectra, which we denote as gamma, is proportional to the power law index of the red noise spectrum. And it's actually a quite simple equation that you see right here. And so essentially what this is telling you is that these 3 simulations, even though the actual morphology of the simulation is quite different, these 3 simulations have a very similar power spectrum when you look at the power spectrum of the structures in the images themselves. And so one thing to keep in mind here, however, is that we're looking at the power spectrum of the image structures, which is different from the power spectrum of the turbulence itself, right? Because we also need to take into account how the turbulent flow is actually going to be emitting light, and then how that light will be affected by the lensing of the black hole. But it's still interesting that even though the images look very different, they have the same power spectrum. And so we also developed a outlier detection method, which is based on PCA. And so we define this metric that's RNL, and it's really a measure of how hard a particular snapshot is to reconstruct. And so if a snapshot has a high RNL, that snapshot is a morphological outlier within the set of images. And so here I'm showing you the results of applying RNL to model B, which again was the model that had the highest variability from the free models that we've been looking at here. And so the dotted line is the light curve of this model. And the colorful curves at the bottom here, these are the results of this RNL metric. So the RNL metric depends on the number of components that you use. And so we're showing you here as an example, the results of using 5, 10, and 20 PCA components. And so there are a few specific snapshots that I want to highlight here. First, this simulation has a significant flare right here. The flux increases significantly, but nothing really exciting happens to the actual structure of the image. Right, so this is what the snapshot looks like for that particular time step in the simulation. And this is what it looks like when you try to reconstruct that snapshot using only 5 PCA components. And so already you're doing a really great job of reconstructing the overall structure of the image. And then when you use 20 PCA components, which is shown on the right here, then you do an even better job. And so there's also this other example snapshot here that is a significant morphological outlier. As you can tell, you have this significant flex tube that's kind of distinct from the region where you usually have emission for this particular simulation. But the actual light curve is not doing anything that exciting. So this is where the flux is right there. And so when we try to reconstruct this snapshot with 5, 10, and 20 PCA components, you can see that we have a really hard time actually performing that reconstruction. It's actually really hard to reconstruct the snapshot because it is an outlier, right? And so the final example is this other snapshot here, which is both a flare and a morphological outlier. So this is what the snapshot looks like. And again, we have a really hard time reconstructing it even with 20 PCA components. And so what I want to talk about now is how we actually implemented this as a image reconstruction algorithm. So what we were looking at before was just applying PCA to one individual simulation, but now we're applying PCA to what I call a simulation soup or PCA soup, where we have a broad range of image morphologies. And so this is a really important aspect of what we're trying to do here, is that we're including simulations in our PCA data set here that are not necessarily consistent with what we expect for this particular source, right? So for instance, for M87, what we did do is we did a cut based on inclination. So we preferred face-on models over edge-on models, but we did not perform a cut based on how thick the disk should be. So we include, for example, simulations like the one that you see right here that creates this really thick disk, even though we don't really expect M87 to look like that. And that's because we're trying to be as agnostic to the underlying model as possible. Right, and so we're trying to make an algorithm that can reconstruct any image that is consistent with the possibilities from a GRMHD simulation, not just reconstruct an image from a particular GRMHD simulation. But of course, there are different ways this could be implemented. You could choose to just compare a particular simulation with VHT data, and that would be fine as well. And so I just wanted to go into a little bit more detail here. So in this figure, we're looking at the exact same time step in the exact same GRMHD simulation. The only thing I've changed here are 2 parameters that are used in the radiative transfer and ray tracing calculation. So one parameter, R high, determines the ratio of electron to ion temperature, and the other parameter, NE, is the electron number density, and that's really just a normalization factor. But you can tell how changing these 2 parameters can really change the image morphology, right? So again, all of these different possibilities would be included in our PCA data set. And so what we did was we included about 30,000 different snapshots, and we tried to be as broad as we possibly could, with the exception of preferring a face-on model versus an edge-on model. And for each of these snapshots, we filtered them with a Butterworth filter, as you can see here. So these would be the original snapshots, and these would be what the snapshots would look like after you filter them with a Butterworth filter. And so these are the first 20 PCA components from this data set. And what I found interesting in this data, in this PCA component set, is that it kind of reminded me of something we had done very early on when we were first learning about PCA. And this was really done just to kind of build a little bit of intuition for ourselves. And so the idea here is that we make a Gaussian move around in a circle, and we treat that as our simulation, and we perform PCA on that data set of images. And this is what the first 4 PCA components look like for that. And so it's interesting that PCA chose to divide the regions where we see emission first into 2, and then it has 2 possibilities where this emission region is divided into 2 that are orthogonal to each other, and then it decides to divide it into 4th. And if you look at the higher order components, it continues to do that. And so these are essentially Legendre polynomials, but it's interesting that this is how PCA decided to perform this dimensionality reduction. And if you compare this to what we see from the actual PCA components from the simulations, specifically, if you look at these 2 components right here, you can see the PCA chose to do a very similar thing. We are dividing the region where we see emission into 2, and we're doing that in 2 ways that are orthogonal to each other. And then when you get to higher components, for example, these 3 right here, you're dividing the region where you have emission into 4, and when you get to even higher, you're dividing it into a larger number. And so it's just kind of interesting that because we are looking at specifically face-on models, what we actually end up seeing for our PCA components does have some resemblance to this very overly simplified simulation that we had earlier. And so everything that I've been showing you so far has been using projections, right? So we are treating our images as vectors, and we project them down to a lower dimensional space. But as I talked about in the very beginning of my talk, the EHT is actually observing the Fourier component of the image. And it's only observing a very small part of the Fourier component of the image. And so what we wanted to see was whether the PCA and the Fourier transform functions will commute with each other. And we were able to prove that they do actually commute, specifically for the implementation that we have. And I'm not going to take you through the mathematical proof, but I just want to take you through kind of what the implications of that proof are in practice. And so, in one case, what we have is that we have this set of images that live in this space, right? And we perform PCA on that space of images, and we derive PCA components as I'm showing you right here. These are the same as the previous slide. And then we can perform a Fourier transform on each of those PCA components to derive the components that you're seeing here at the bottom. The left side is showing you the amplitude of the Fourier components, and the right side is showing you the phase of the Fourier components. And on the other hand, the other option, or the other path that we could take, what you would do is you would take the Fourier transform of each and every image in your space. So now you have a space of Fourier transforms of images, and then you could take the PCA of this new space, and you would end up with the exact same amplitude and phase for your Fourier components. And so what this means in practice for our algorithm is that we can perform PCA on the images from these simulations, and we use that to derive our PCA components. And then we can take the Fourier transform of those PCA components, and those are what we use for the actual fit to EHT data. And so this is what this bottom equation here is showing you, is that we can use the Fourier transform of these components in a linear combination where we are deriving the different amplitudes for these different components. And that's what we're really comparing to EHT data. But those same components those same amplitudes, can be used to actually reconstruct the image in the image domain as well. And so if you remember this geometric model fitting slide, right, this was our hard snapshot from before that we were not able to reconstruct with a geometric crescent. So this is the snapshot that I want to use as an example to show you the results of using these PCA models to actually fit to simulated data. And so here's the same snapshot. I've just flipped it over due to some, it's just a preference. And here's the filtered snapshot, right? And this bigger image over here is the result of fitting this snapshot with only 20 PCA components. And I've overplotted as contours the original snapshot so that you can compare the result from this fit with the original snapshot in more detail. And as you can see, there are a few really exciting things about this fit. So first, we do not have any significant bias in the overall size of the image. And we are able to reconstruct this really significant feature that you see here, right? So in this particular fit, we have the free parameters that correspond to the amplitudes of the Fourier components, but we are also allowing all of the components to change in size. So we have an overall scale parameter that we also allow to vary. And we also have an overall rotation parameter that we also allow to vary. And so all of those parameters are still only about 20 to 20 free parameters. And so it's really still a small number of parameters, but we're able to reconstruct a much more complicated source structure. And this is what the actual fit looks like to the simulated data. So we're doing a really great job with the actual fit, and our residuals are looking really great. And so to look into this with just a little bit more detail here, this is what happens when you look at the cross sections of these images. So the dotted lines correspond to the analytically calculated boundaries of the black hole shadow. And the blue curve corresponds to a cross section of the original snapshot. And then the orange curve corresponds to the same cross section, but taken from the fit to the simulated data. And so the first thing you can notice is that we don't have any significant offset between the peak of emission in our fit relative to the location of the black hole shadow. And so that's really exciting already. And of course, we are broadening the emission profile significantly, but we're still doing a really great job in terms of keeping as much of the structure as we can. And so the pros for this new method, so first we still have a small number of parameters, as I've been talking about, and we do not create the artifacts in the images that you would see, for example, from the imaging algorithms. And we're also able to reconstruct more complicated source structures than what we can do with the geometric crescent models, and we don't introduce the same biases that you see with the analytic crescent models. And so we're also not limited to comparing to specific realizations of the turbulence. And so we can reconstruct images that are not contained in the original simulation data set as well. And so of course, there's always some pros and cons, right? So the drawbacks are that this is not model agnostic. So you are baking in at least some information about these GRMHD simulations, but we tried to be as agnostic as possible by including a really broad range of simulations, even if they didn't actually fit our predictions for M87. And you also need to create a fairly large simulation training set. And so in summary, PCA can be used in many different ways for data analysis. So you can use it to probe the power spectrum of the structures in the images. You can use it for outlier detection. You can use it to characterize the variability in the simulations. And you can also use it to fit to data so that you can reconstruct images that lie in the same general space as simulation images, but are not necessarily equal to any of the simulation images themselves. And the other thing I want to remind you all of is to please fill out the survey. It is very important for us to have that information from you guys. It helps us to improve these webinars so that they can be more useful for you guys. So please do fill out this survey. It will only take you a couple minutes. And with that, I'll take questions. Thank you.
Thank you very much, Lia. And I just posted the link to the survey on the chat for everybody to see. Please do fill the survey before you leave or as you're leaving, because it's really, really important for us. And now is a wonderful time. Thank you, Lia, for being perfectly on time. We have a few, like 7 minutes before the hour. So please put in your questions in either on the chat or on the Q&A. And to get the discussion going, I have a question actually related to the last bullet that you have. When you first look at interferometric data, you don't know a priori whether they're anywhere near the types of images that you think they might be, right? Our simulations could have been completely wrong, and the image of a black hole looked like, something very, very different. What would have happened had we tried to fit that data with, or what would happen if we tried to fit data that do not look like what we think black holes are with a set of PCA images that come from a simulation based on our prior expectations?
Yeah, so that's a very good point. So we are able to reconstruct images that are not contained in our data set, but are still kind of consistent with the broad morphology that we see from these GRMHD simulations, and that's fine. But if you have a completely different image that it's, let's say a black hole actually looks like a dog, that's going to be a much more difficult situation. And so we're going to be in a situation where we are trying again to fit a model to data that is not really a good model for that data. And so my expectation is that you'd probably not get a very good fit. So you might be able to tell that you're not really doing a great job actually fitting the data, depending how different it is. But if it's similar enough that you'd still be able to get some fit, even if your chi-squares aren't great, then yes, that would be a concern that you might be able to potentially fool yourself if the source image is kind of in the sweet spot of similar enough that we can still get a reasonable fit, but different enough that we're going to end up biasing our results. And so that's, again, one of the reasons why I always say that this new method is really complementary to the other methods. And so that's why it's so good that we have these different ways to approach this, this problem, right? And so we can compare the results of our fit to, for example, results from image reconstruction with the more general imaging algorithms. And if we have a situation where the results from the imaging algorithms are very different than the results that we get, then we would be very suspicious of our results, of course.
Thank you. So we have a couple of questions coming in. The first is from Aviat. Thanks for the great talk. In the hard snapshot example you showed at the end, did you fit the image directly, or did you use the Fourier components to fit EHD data of the snapshot?
Yeah, so we did perform a simulated observation. We included errors and noise and all of that as well in the simulated observation, and we did fit only to the simulated observation. So we only use the visibility amplitudes in the closure phases specifically to perform that fit. And we were using the baseline tracks for M87 from 2017.
We have a question from Ramesh. These are very impressive results. Can this method be used to compare data with different simulations, for example, different black hole spin values, and identify which is the best match? How would this work?
It's a very good question. So I don't have an extra slide, but I'm going to try to describe what these figures might look like. So if you remember that I also applied PCA to different black hole shadows for non-Kerr black holes, one of the things that we included in that paper was a plot that's showing you how the different metrics, or in other words, the different ways in which you can modify away from the predictions of general relativity. Each metric tended to create shadows that would kind of live in a particular region of the first amplitude versus the second amplitude parameter space. So the idea here is that you're looking at the amplitudes of the Fourier components, and you're comparing whether different simulations have significantly different amplitudes for their Fourier components. And so what we were able to show using these non-Kerr shadows is that when the parameters that determine the amplitude of these perturbations are quite small, the regions where these different metrics live overlap with each other. But when you get to bigger deviations to your black hole metric, then you can have each of these metrics live in a distinct region of this, amplitude versus amplitude parameter space, where you're comparing the amplitude of like the first and the second PCA component, for example. And so we've looked at that same idea for these simulations. But for the same reasons why it was hard for you to pick out which of those 14 snapshots was different from the others, right? For those same reasons, what we end up seeing is that the regions where different simulations live tend to overlap. And so there is, there will be like an offset, for example, between sane versus mad, but the regions will be two overlapping distributions. And so we might be able to argue for sane versus mad when you have a situation where your particular realization of turbulence is in a region that would rule out one of these possibilities, but it's more likely that you're going to end up in a situation where you're still going to be broadly consistent with both sane and mad. But it's important to keep in mind that the fact that that is true actually tells you a lot about how the structure of these images does or does not depend on these different parameters, right? And so it's something that we're definitely looking into, and we're trying to figure out different ways to do this, but it's already really significant that these different distributions are generally overlapping with each other. So thank you, good question.
Very good. Any more questions? We're just hitting the hour mark. I'm putting one more time the link for the survey. And I would like to thank Lia here for a very, very wonderful presentation of a complex topic. And thank everybody for attending, and all our previous speakers for this series of webinars, and hope to see everybody again in the fall for the next series of webinars. Thank you very much.
Thank you all for coming.